Hi and welcome to Geeks for Geeks. I'm Siddhartha Hazra and today we would be discussing a very interesting problem that is kth largest element in a BST. So let's talk about the feedback of this problem. If you have solved an easier version of this problem, that is kth smallest element in a BST, then it is a little bit on the easier side, and this problem I can say it is a little bit above, like 1.5 level of the kth smallest element in BST. So let's understand this problem itself. So as you all know, binary search tree is a tree which facilitates the searching of an element where the left side of the tree is smaller than the root and the right side of the tree is bigger than the root. And this property is valid across all the nodes. This was a basic explanation of binary search tree, and what this problem demands is, given a binary search tree, you need to find the kth largest element. Okay, so at this point I would tell you a fact that you kind of need to understand as well as you need to remember in your further questions. Okay, the fact is, in order traversal of BST gives a sorted array. Gives a sorted array, like a sorted result. You don't really need to mention is sorted. So this is the value that you need to understand. This is the thing. So after knowing this fact, now I would consider that you know this fact. Okay. So after knowing this fact, if it was given kth smallest element, what you can really do is you can start having an in-order traversal. You can print the kth element itself, and that would be your result. Okay. Now the very next thing is, in the same manner, what you can do is to print the kth largest from the back. You can just go from the back and you can start counting 1, 2, 3, 4, 5, and when this value is equal to k, you can print that. For instance, let us understand this very first sample test case given 4 to 9. Or let's take a big value. Let's first under the sample test case, and I want the second largest element. Doing the in-order traversal would be 2, 4, 9. So second largest element from the back would be 4. Okay. So now let us see this binary search tree. Let us draw some quick examples at this point. Okay. Let's say you are given a binary search tree as 8, then it is 3, then it is 1, then it is 6, and this side it is 10 itself. Okay. So if I do an in-order traversal, what is in-order traversal? Left, root and right. So the very first value would be left, that is 1. And then we move forward to root, that is 3. Then we'll go to right, that is 6. Then after this left side is visited, we would visit 8, that is 8. And then the right side, that is 10. If you observe, this is the value. If let's say for instance k third largest element, we would start from the back 1, 2, 3. When this current index from the back is equal to this, we would simply say yes, this is the value. So if you want a short and a concise explanation, this is the result itself. Okay. So now what I can do is I can simply, so as you know, visiting the binary search tree in this fashion, that is left and then root, and then if we visit the right part of it, it would give me the sorted value. So if I interchange this position, that I know that the right part would be the largest. So if you observe, the right part is the largest. So if I prioritize on this right part and the left part would come here, let's see this. Now we would visit in this scenario, we would visit in this fashion that right root and then it would be left. Now let us visit the same thing again. Let us remove some of the annotations. It would be a bit clear. So now let us start visiting it. So roots right is 10. So it would be 10. Then root, that is 8. Then after left and root is done, then we would go to left. So so root, this values up till now, right is not visited. So we would first go to the right part of it, that is 6. Then we would visit the root, that is 3. Then we would visit the left, that is 1. So if you observe, this is giving me a reverse sorted order, that is a decreasing order. And this is correct. So from the front, I can just go to the kth element and I can just print that. Okay. And I can solve up this problem by doing a reverse in order traversal. Now to make things more interesting, okay, so the auxiliary space here is big of H, but can we do it without using any auxiliary space, like without keeping that in a particular vector or something, without keeping this and counting this? Yes. If you observe that we are visiting elements from the back, so the first element would be equal to the first, then second, then third. We just are concerned about one element individually. So what we can do is, we don't really need to save the values at the end, go to the kth element and leave all the values. So all the other elements are unused. See, what is the use of saving these all result? Whatever be the result, I am not concerned about all this. So what I can simply do is, while I am traversing, while I am visiting, I can keep a count. I know that they would be visited in the reversed sorted. So when I am visiting the first element, I would make a counter of 1. When I am visiting the second element, I would make a counter of 1. When I am visiting the third element, I would make out a counter of 1. And when I am visiting the kth element, when the current visit is the kth one, I can simply consider that element. Now to make things more simpler, what I am trying to do is, whenever it is the kth element, I am adding that value. Rest, I am leaving all the values. Okay, and everyone else is returning 0. Only the kth element is returning some element, so the value would always be 0. And it is told the values and all would be less than equal. So now let us start with this consideration. So at this point we would do a reverse in order traversal. We would maintain a variable that is known as k. We would pass by reference and we would keep incrementing it. Whenever the particular value hits the desired value, then we would say yes, add this value, rest all, leave all those values. So I would say, I would name it as recursion rec. Okay, what all I need the node star r, a lazy person as you know. Then I would need the information of the kth one. Okay, like what is this desired value, and I would keep a counter like how many elements I have visited up till now, and this value would be passed by reference. Okay, so that it doesn't change. Now I would say, if r is equals to null, then I don't want it to modify the result. Okay, I don't want it to modify the result. So adding a 0 to the result won't affect. Adding a 0 to the answer variable won't affect. So I would simply return 0 at this point. Then I would initialize a sum as 0. Okay. Now at this point, first I would go to left, root, right. So reversed one would be right, root, and then left. So sum plus equals to rec of r dash right and then it would be k only, and then this would be equal to c. At this point, after the right part is done, then only we would visit the root. At this point, we would update the counter. And now after updating the counter, if it is equal to the desired value, then this needs to be considered at this point. So I would say sum plus equals to r dash data. Rest all we don't really care. When the visit count is equal to k, we would only consider that. Rest all values we would ignore or add 0, so that the answer is not affected. At this point, I would say sum, like I can simply copy up this value so that it is not affected by anything, right dash left, and then we simply return the sum. See how cunningly I have added 0 in all other cases and adding that value in that particular case, so that the answer is not affected. Okay, we are returning sum. So at this point we would initialize a variable as 0, and then we would simply return the value that is there. So I would say root comma k comma c itself. Now let us compile and run and see how many errors are we making. Okay, seems like no error is being made. So yes, there might be easier implementation too, and this implementation is not akin to the editorial implementation. So this is what I found the most intuitive one. Yes, you can use C without pass by reference, but the space and the time complexity would be absolutely the same. One small optional optimization that you can perform if you are considering this question above an easy problem, then you can stop when C is equals to T. At that point, you can simply return the call. Okay, you don't really need to move forward. Okay, this was the small optimization. Other than that, the time complexity would remain the same, only the implementation styles would differ from person to person. So that's it for today. If you like this video, consider liking and subscribing of this video so the reach of this video could be increased and this work could be justified. That's it for today. This is me, Siddhartha Hazra, signing off. Thank you.